Can everybody hear me? Okay, some of you are saying yes. Again, I have you all muted to avoid feedback. If you don't see your mic muted, please do me a favor and mute your mic. Otherwise, we'll get a lot of background noise. Okay, let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9. We are waiting for one person to join us. I'm trying to see who that is. Okay, we'll wait another minute to get started. Okay, just so you know, I am recording this meeting. And again, the idea is we'll have it finalized in about a day, and I will share the link with you, okay? Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. I think you all made it over. Congratulations. Okay, I'm going to end the other meeting in Canvas, and then we'll get started with our meeting here. Again, just so you know, our meetings will be in WebEx from now on, okay? So all meetings will be in WebEx from now on. Okay. Okay, again, I'm just terminating the other meeting because I'm not sure if my internet bandwidth can handle two at the same time. I'm trying to figure out how we should begin. And I'm thinking I'm going to try sharing my screen with you. Again, I apologize for me having to check and ask, but since it's a new platform, I want to make sure it's working the way I think it should be working, okay? So today we are going to start talking about what's called the fundamental counting principle and counting using permutations and combinations. This corresponds to the sections in our textbook 8.1 and 8.2. Okay, one way that we can do this is we can walk through the slides or we can walk through my notes, okay? Some of you have used the notes that I've uploaded to the course. So let me ask you what you prefer, slides or notes. Okay, that's what I'll share with you. Okay, so please respond in the text box. What do you prefer, that I walk through PowerPoint slides or notes? Okay. All right. Well, it seems to be an overwhelming decision for the slides. Again, I truly apologize, Danae and Tabitha, since you wanted the notes. How about this? I'll start with the slides and then basically move to the notes. Okay, we had someone new join us, and the question is this really going to go on until 11:15? And the answer is no. Okay, basically, I set aside more than enough time to cover the material. Usually we have a 100-minute class, an hour and 40 minutes. So I hope to end earlier. And basically, I just blocked off a 2-hour chunk because I wasn't sure if WebEx automatically terminates your meeting, and I didn't want that to happen in the middle. Okay, so I set aside a too big chunk. I am recording the meeting, and so I will upload it, as I said before. If you need to drop off at any time, please feel free to do that. Just remember, go back to our My Math Lab course and look for a new section on that left-hand navigation bar that has our recorded conferences. And I will make that really clear. I will send out an email to everybody. So don't worry that you won't be able to find it, okay? And again, you're always, always welcome to email me and ask me questions about anything, okay? All right, so let's start with the slideshow. And let's see where that is. I'm going to try to share my screen with you, okay? And hopefully that will work. Let's see how I can do this. Okay, slides. Okay, share. I have two choices. One says screen, one says applications, and the application says beta. So I am going to share my screen. Okay. Hopefully. Click. And it says my entire screen, yes. Okay. All right, and now I'm going to move to the slideshow. Okay, hopefully everybody is hearing the slideshow. Is that everybody seeing the slideshow? Okay. Okay. Again, unfortunately, I can't see your chats while I'm sharing. So I'm going to have to stop sharing briefly. Okay. Just to see that everybody is seeing it okay. All right. Hold on. Maybe all I need to do is, okay, good. Everybody was able to see it. So I'm going to start sharing again. And I think all I need to do is toggle between the windows. Okay, so here we go again. All right. So again, we're starting section 8.1, and this is talking about the multiplication principle using permutations and combinations. But let's talk about what we're doing here, okay? We're heading towards trying to compute a probability, all right? And you know from probably just a general sense of what probability is, you're going to need to count the number of possible outcomes for your event, okay? And you're also going to need to count the number of ways the event you're interested in can happen. In a simple way, if I'm drawing a card from a standard deck, you know there are 52 cards in the deck, right? That's the total possible outcomes of the draw. And if I'm interested in the probability of drawing an ace, you know there are 4 aces. So those are the number of outcomes I'm interested in. Okay, so this chapter, chapter 8, is going to talk about more complicated ways to do counting when, for example, you're selecting more than one thing out of a whole bunch of things. Okay, so a more complicated choice. It's going to start out simple, though, with this multiplication principle. And it's pretty intuitive. It basically says if you're going to make a series of choices and you want to count the number of ways that series can happen, all you have to do is multiply the outcomes of each choice in the series together. Okay, that's the multiplication principle. So let's take a look at the slideshow. And again, I'm going to go back to the WebEx meeting occasionally. and we can talk about what we see. I'm going to see what works well as far as sharing information. I do have a whiteboard with me, but I kind of have a feeling, given the quality of the video, it would probably be better if I just type on a Word document and share that. So let's see what works. Okay. Thank you for your patience. All right. So, gosh. Okay, so I'm trying to see what I'm missing here. Page 261. It's not scrolling the way I expect, so I'm going to have to do this. Okay. All right, so here's the multiplication principle, and it basically says if you're going to make a series of choices, n choices, and each one of the choices has a different number of possible outcomes. Okay, so first choice, let's say there's M1 ways to make it. Second choice, there are M2 ways to make it, and so forth. Where the last choice, the nth choice, has N ways to make it, M sub N ways. Then what you do is you're going to multiply these number of choices together to figure out how many ways there are to make the whole sequence of choices. Okay, let's take a look at an example. Okay, here's a combination lock example. Now, some of you probably have experience with these types of locks. They're the kind of lock that you would have on a locker in high school or a locker at the gym. And they have little dials on them. Okay, so let's say that our combination lock will open if I set the right number on each one of 4 little wheels. Okay, so that's what it means. A combination lock can be set to open to any 4-digit sequence. Part A is asking us how many sequences are possible. Well, if you look at what they say for part A, okay, there are 10 possible digits that you can set on each wheel from 0 to 9. Okay, that's 10 choices. And there's no law that says you can't set the same digit for each one of the wheels. That probably makes for a bad combination. But if you really want your combination to be 9999, there's no law saying you can't do that. Okay, so by the multiplication principle, you've got 10 choices for the first wheel, 10 for the second, 10 for the third, 10 for the fourth. If you multiply all the 10s together, there are 10,000 different sequences. What you want to understand about this part A is, in part A, we're allowing you to sample with replacement. Okay, this is a very important concept in probability and statistics. Okay, in other words, what that means is once you use a digit for the first wheel, you put it back in the allowable digit pool for the second wheel, and the third wheel, and the fourth wheel. Okay, so essentially, you're sampling without replacement. You can pick any one of the 10 digits for each of the wheels. If you take a look at B, how many sequences are possible if you don't repeat a digit? That's a little bit different, because once you choose a digit for the first wheel, you're not going to be allowed to use it anymore. Okay, so let's say I pick an 8 for the first digit in my combination. I can't use it for the second. So now I only have 9 choices for the second wheel. Suppose I choose a 1 for the second digit in my combination. By the time I get to the third wheel, I've removed 2 possible choices, the 8 and the 1. So now there are only 8 choices left. Okay, and so forth, right? You can see 8 choices for the third digit. Whatever I choose for the third digit, say it's a 5. Now I have 8, 1, and 5 removed from the pool. So there are only 7 choices for that last digit. Is that clear to everybody? Can you just type in the chat whether or not that makes sense to you? Okay. Okay, everybody's good with that? Great. I'm going to go back to the PowerPoint. Okay, so if we're choosing without replacement, that's part B, where once we choose a digit, we can't use it again. You can see we get this interesting pattern. We get 10 choices for the first, times 9 for the second, times 8 for the third, times 7 for the fourth, okay, which is only 5,040 choices. You can see up here, when we chose with replacement, we get a lot more possible outcomes. This is 10,000, and this is about half of that. Okay, so you can see choosing without replacement does cut down on the possible outcomes. Okay, let's take a look at this diagram, and I'll give you a story to go with it. Okay, again, let's say you're choosing a breakfast. Okay, so a breakfast consists of, if this is your favorite restaurant, let's say the breakfast consists of a pastry, which can be either a bagel, a muffin, or a donut. Okay, that's what B, M, and D stand for. And then you're allowed to have a beverage, and you have two choices, either coffee or juice. Okay, so in this restaurant, you've got a choice of a pastry for breakfast and a beverage, and maybe that's their special. You get both of them for, I don't know, let's say $3. So the question is, in how many different ways can you choose breakfast? Well, if you look at this decision tree, you can see I can choose a bagel with either coffee or juice, or I can choose a muffin with either coffee or juice, or I can choose a donut with either coffee or juice. You probably remember from the stuff we did in chapter 7 that each one of the branches in this decision tree is an or, right? So bagel or muffin or donut, and out here, coffee or juice, coffee or juice, coffee or juice. So the way you count the number of possible $3 breakfast specials you can make is to count the number of terminal ends here of the tree. So you can see I have 1, 2, 3, 4, 5, 6 possible 2-item breakfasts. Okay. And that's really, if you think about it, is the multiplication principle. There's 3 choices for the pastry times 2 choices for the juice or the coffee, right? 2 choices for the beverage. And all we do to get the total possible outcomes is to multiply those 2 choices out, those number of outcomes together. Okay, so 3 times 2 gives me 6 possible outcomes. Okay. Everybody okay with this multiplication principle? Okay, choice 1 times choice 2, and we wind up with 6 possible outcomes. Everybody good with that? Okay. All righty. Let's take a look at another example. Okay. So a Morse code, for those of you who might not be familiar with it, is a code that was developed for use in the middle of the 19th century with a telegraph. Okay, a telegraph was invented around 1850. It was a precursor to the telephone, which didn't show up until around 1875. And the Morse code allowed you to send a series of signals over a wire using dots and dashes to represent the letters and the numbers. Okay, now this might seem pretty primitive, but think about it. At that time, your only alternative was to probably the fastest way to send a letter was by Pony Express, which was a handwritten message given to a writer who went on a horse and delivered your letter that way. Okay. Eventually, the mails were handled by cross-country railroad, but that didn't happen till I think 1859 or 69. I think 69 was the cross-country railroad. So Morse code predated that by a bit. Okay, and it allowed very fast transmission of messages. It was primarily used on the railroad to warn of a dangerous situation down the track. Okay, so if your Morse code had basically at most 3 symbols, okay, so dots and dashes could represent letters and words, okay, so there were 2 choices for each symbol, right? It could either be a dot or a dash, okay? So let's see how many possibilities there were for one symbol, okay? This could be, say, represent a letter, okay? So if I had a dot or a dash as a possibility for the first symbol, there's 2 choices, okay? If it's a 2-symbol word, I have dot dash, or 4 possible choices. And if it's 3 symbols, I have dot dash choices for each of the 3 symbols. So there's 8 possible words you could make in Morse code there, okay? So altogether, if you wanted to add these up, you'd have 2 plus 4 plus 8. There'd be 14 different sequences with up to 3 symbols in them. Okay, so it was fairly limited, but it did the job. Okay, and again, I'm kind of just showing you possibilities for using this multiplication principle. Okay. All right, let's see what's next. Okay. Okay, here's an interesting one. Let's look at this one. Okay, a teacher is lining up 8 students for a spelling bee. How many different lineups are possible? Well, there are 8 students to pick from, but let me ask you this. Once a student is chosen to stand in a certain place in line, can that student be chosen again to stand in line? What do you think? Can I choose a student twice? Okay, so I'm asking you a question in the chat. What do you think? Okay, I would say no, because again, we're lining students up to be in a certain order, right, for the spelling bee. Okay, so let's put yourselves in the situation. I would say that's correct. A student can't be in 2 places at one time in the line. But my question to you is, so does the order matter? Okay, if you're lined up in a spelling bee, if you have any experience with that, do you think the order you're in matters? Okay. Okay, that's fine for now. Okay, we'll pay attention a little bit more to order later, and we'll spend a little more time trying to determine when order is important and when it's not. But usually with a spelling bee, basically the way it works is if the person ahead of you misses a word, you get to spell it. So I'm not sure whether order is important or not. Okay, but let's go back to the PowerPoint slide and see what they say. Okay, so we have to make 8 choices, 1 for each space that will hold a student, and any student should be chosen for the first space, so there's 8 choices for that, then 7 for the second, okay, since 1 student has already gotten a space, 6 for the third, and so on, okay? So here's the multiplication principle showing you how many possible choices there are for all 8 spaces in the line. Do you see this pattern over here on the left? The 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1? Okay. You can see that even though we're only starting with 8, when you multiply in that way, the number gets very large very fast. Okay, this 40,320 is the total number of ways we can arrange those 8 students, right? Because I can pick any one of the 8 of them for the first spot. than any one of the 7 who are left, right? So there's that many different ways to arrange them, okay? But again, this pattern is very important. It shows up again and again and again in probability, okay? And it's starting with a given number and then multiplying by one less every time until you get down to 1, okay? That actually has a special name and a special symbol in math, okay? So let's see if they go into that in the next slide. Yes, okay? Basically, this is called a factorial, okay? So on this last slide, this 40,320 is 8 factorial, okay? And here's the way it looks, okay? N factorial, where N is a number, the factorial symbol looks like an exclamation point, okay? An exclamation point is on your keyboard, so you can certainly type that into my math lab. And what it means is take the number and multiply by 1 less, then 2 less, then 3 less, until you get down to 3, 2, 1, okay? By definition, we're saying that 0 factorial is a 1. I know this seems kind of strange, okay, but the factorial notation won't work unless we make that allowance, okay? So let me show you how you can do factorials, okay? So I'm going to step away from the slideshow for a while, and I'm going to show you how to do this on your TI, as well as how to do this in Excel, okay? So can everybody see me clearly enough that if I hold up my calculator, I can show it to you? Okay, everybody see my TI? Okay, again, I know it's not very bright or very big. Okay, so here's what we're going to do. We're going to select math. Okay, then turn your calculator on, select math, then arrow over to PRB. Okay, it's either PRB or PROB. Okay, everybody get there. Okay, here's what mine looks like. If you can see it, I don't know if it's visible because there's a lot of light on the screen. Okay, when you get to PROB, okay, selection 4 is the exclamation point. Okay, everybody see that? That's selection 4. Okay, everybody follow? So the way you have to do this is type in a number. Okay, so quit out of where you are, type in a number, then math, PROB, factorial. Okay, so type in a number. Now let's see, why don't we all do the same number? Why don't we type in 8? Okay, so here's what I'm telling you to do. Type in an 8, then math, PROB, factorial. Okay, I'll do it with you. Okay. Everybody getting the same number as on the slide. Let's try a different number. Try this one. Whoops. Okay, everybody try it with a 10. Okay. All right, good. Everybody's getting the right answer. That's excellent. Okay. You can see that these grow very quickly. I want to show you something that happens with your calculator that's not a problem, but I just want you to be aware of how fast these numbers grow. Everybody's getting the 3,628,800, which is correct. Okay. So now try this one. Try that one. Okay. All right, I'm going to wait for a couple of other people to try it. Give it a shot. Okay. What do you think overflow means? Okay, everybody's getting an error. That's good. Again, I wanted to show you these numbers grow very fast. Okay, what do you think overflow means for your calculator? Anybody have any ideas? Excess, okay. That's one good idea. Anybody have any other thoughts about overflow? What happens when a bathtub overflows? Overfull, okay. Or it could mean too much water, right? So in this case, what it means is the number 70 factorial is too big for the calculator to hold. Okay. Believe it or not, your calculator has size limits. Okay. And 70 factorial is over that limit. Okay. So again, no big problem. All you have to do is quit. And again, we typically won't be using factorial by itself. Okay. We'll be using it embedded in other things. Let me show you another way to do factorial since some of you are more comfortable with Excel. I'm going to bring up Excel now. Okay, hopefully everybody can see my spreadsheet. Okay, and all of these probability functions are built into Excel. Okay, the function for factorial is called fact. Okay, and it takes a number. Okay, so I'm going to say equal because I need an equal sign to run a function. And then you can see fact. So I'm going to type in fact. And again, it says returns the factorial of a number. Okay, so I have to put in, when I open parentheses, it tells me what it wants. So I'm going to put in the number 8. Okay, what's 8 factorial? We already know that, right? So there's my 40,320. It winds up in the cell, but if you click on the cell, you can see the formula up here in the function box. Okay, let's do the one for 10. So equals fact 10. Okay, and that should be our 3,628,800. Okay, so again, just showing you that you can use Excel if you prefer. You can use your TI-84 if you prefer. Okay, not a problem. Okay, anybody, any questions about the TI or Excel? Okay. Okay, Hilsey, what's your question? Okay, please type in your chat box. Okay, all right. E100. Do you have a TI-84 or do you have a more modern calculator? Okay, what Hilsey is saying is she didn't get an overflow, but look at the exponent on hers. Well, she has the app. Okay. The app is more modern. Okay, and so it doesn't overflow at as low a number. But it will eventually overflow. No, the E means 100 zeros after the number. Okay, so what she got was 1.197, let's just say. Okay, and then 100 zeros after that. Okay, E means it's in scientific notation. Okay, so it's like 1.197 times 10 to the 100th. Okay, so again, if you have the app is a more modern piece of software. It won't overflow as fast. Okay, but if you're using the physical TI-84, the biggest exponent it can handle is 99, which is why this number overflows it. Okay, any other questions? He'll see, did I answer you? Okay. Any other questions? Okay. Again, feel free to use whatever works for you. Okay. Again, in this online environment, you're now able to use Excel. Okay. For anything you like. You can use it for homework. You're always able to do that. But now you can even use it on a test because you've got it and the tests we're now in this online environment. So I would rather you learn how to use as many tools as you have out there. Okay. Anybody, any other questions? Then we'll move on. Okay, so there's factorial notation. I am going to move down a bit. Okay. Okay. This next slide, I'm sorry that they jump. I can't control that. I'm introducing this concept of a permutation. Okay. A permutation of n things taken r at a time. Okay. We're basically saying when you take a permutation, you're saying that order matters, okay, and you're sampling without replacement, okay? So for a permutation, order matters and you're sampling without replacement. Let me see if I can bring up a Word document. Okay. Okay, order matters and you're sampling without replacement. Okay, so in general, think of our spelling bee students. Okay, we're choosing 8 out of 8 of them. Okay, we're choosing 8 out of 8 of them. We're sampling without replacement because nobody winds up in line twice. Okay, and I would say the order they're in line matters. Okay, because basically whenever you're standing in a line, there's usually some inherent order in the line. Again, to use a very timely example, suppose you're lined up outside Fry's just as they get their new shipment of toilet paper, and you are the first person in line. Okay, I think that it matters whether you're the first person in line or the 50th person in line. Okay, so what would you say to that? Do you think when you stand in line, order matters? Okay, I'm just kind of polling you a little here. Usually I use the example, somebody's waiting for concert tickets. And yeah, Joanne, very good. First come, first served. And nowadays it's especially relevant. Again, if you're waiting in a line to buy scarce goods, it does matter whether you're first or whether you're 50th. So in all the problems where you're in a line waiting for something or whatever, if you're served in that order, okay, then let's say that order matters, okay? So in our spelling bee example, we're going to say the students are in a line where order matters. I don't know about you, but I wouldn't want to be the first person to spell a word in the spelling bee, okay? So anyway, we're going to say that these two conditions hold for our spelling bee students, okay? So what that means is I can count outcomes with permutations. Okay. So basically, I'm going to count with N, P, R. Okay. And in this example, N is the total number of students, which is 8. And R is the number who will stand in line, which is also 8. Okay. Everybody all right with that? So the N value is always the same size or bigger than R. It is never smaller. If you ever type in a permutation like that and you put, you reverse N and R, you'll get 0 for your answer. Okay. So in my example, I want to type in 8P8. Okay. Now I know they showed you this formula here in the slideshow. Let's see where that is. See this formula? We are not going to use the formula, okay? But if you were to use the formula, you would have 8 factorial on the top, 8 students I'm picking from, and then I'm going to use all 8 of them, so R is also 8. So I have 8 minus 8, which is 0 factorial, and we said that was 1. So this is just going to give me 8 factorial, okay? But I want to show you how to do it on your TI-84. Okay, so here we go. I'm coming back to your Zoom conference. Okay, so here's what I want to show you how to evaluate NP8. Here's the way we're going to do it. On the TI, we're going to do it the same way we did. Type 8, then math, prob, and then you're going to choose NPR, which is in your probability menu. It is the second choice. And then you type your R value. Okay, everybody got that? Okay, here's how you're going to type it in. I want you to try this. Type 8, then go to the same menu where we had factorial, okay? And then we're going to type in the other 8. So I'm typing in 8, math, prob, NPR, and then 8. If you have the new software on your TI, you'll notice the 8s turn into subscripts, okay? But you should have gotten the answer that we saw in the slideshow before, which was 40,320. Okay. So going back to our meeting. Okay. Again, I want to make sure that we're comfortable with uh, permutations. Okay, good. Good, good. Okay. So how does having the Word document, does the typing in Word work for you? Okay. It's either that or a whiteboard, and I'm not so sure you'd be able to see the whiteboard. Okay, typing in Word work for you. Good. Okay. All righty, let's go back to the slideshow then. Okay, so as you see, we're not going to use this actual formula. We're going to either use the TI, or if you're more familiar with it, I'm going to bring up Excel again. Okay, remember, here are our factorial examples. Okay, over here in column C, I'm going to use my permutation. There's a permutation function in Excel, equal, it's called permute. Okay, and it returns the number of permutations, right? As soon as you type in parentheses, it'll tell you what the arguments mean. Okay, in our example, we had 8 students, comma, and we want to choose 8 of them. Okay, so there's our 40,320. Okay, and you can see that turned into the same thing as 8 factorial, because in the permutation formula, our denominator was a 1. Okay, so again, hopefully everybody is okay with either doing this in Excel or doing this in the TI, okay? Okay, make sure you're okay with at least one of those, preferably both. We're good? Okay, good. All right, I'm going to scroll down a bit. Again, I'm showing you this one, okay? So a teacher wishes to place 5 out of 8 books on her shelf. How many arrangements of 5 books are possible? Now, you have to understand, this is a bit of a contrived problem, because to be honest, nobody would just dump all the books on the floor and then randomly pick them up and arrange them, especially if the order of the books mattered. But what they want you to imagine here is the order that the books are on the shelf is important, but the teacher is going to randomly have 8 books on the floor, and she's only going to pick 5 of them to put on the shelf. Okay. So she's picking without replacement. Okay. Because once the book is on the shelf, it's not going to go back into the pile on the floor. Okay. And we're assuming that the order the books are on the shelf matter to her. Okay. Just like the order of the books in the on a shelf matter in the library, right? So she has 8 ways to fill the first space, 7 ways for the second, 6 ways for the third. Essentially, what they're doing here is they're counting with permutations, but N and R are different. Okay, in this example, she has 8 books to choose from, so N is 8, and then she's only choosing 5 of them, so R is 5. Okay, so this number, okay, you can either logic your way through and you can say, all right, 8 possibilities for the first, 7 for the second, so forth. When you get to the 5th space on the shelf, there's 4 books left. Okay, and you get this to be 6,720 arrangements. Okay, that's the same thing as 8P5. Okay, so let's try that. Okay, the book's on a shelf. Okay, so let's say I have 8 books to choose from. Picking 5 of those. And order matters. Okay, arrange. This is, I'm going to say arrange books. So basically, you know, it's without replacement, right? Okay. So here's what I want you to do. I want you to compute 8p5. Whoops. Okay, so you can either do it on the TI, okay, or you can do it on Excel. So I'm asking to you try. Okay, what's 8p5? Okay, it's to make sure you know how to get back to the right menu. Okay, I want everybody to give it a shot. Remember, it's math, PROB, NPR, okay, and then you put in the 5. Okay. Okay. Okay, we're all getting 6720. Okay, good. And again, your choice as to whether you use Excel or the TI. I'm okay with either one. Okay, whatever works for you. If you look on the internet, there's even some apps you can find that are, you can just type in permutation or combination calculator and you'll find those. Okay, so anything goes as far as calculating these. I'm all right with it. Good. Okay, so that's a permutation. Let's see if there are any more interesting examples in the slideshow. Okay. Okay, we've got books. We know that because we just did 8, 8, and we got 8 factorial as the answer. Okay. They're actually going through the calculations in the slideshow, which I don't want you to do. I want you to use your TI or Excel. So I'm scrolling through this to see. Here's an example that I do want to share with you. Okay, this example is called non-distinguishable permutations. Okay, so let me write that down. Okay, non-distinguishable permutation. Now, what does that mean? Okay, if you look at the word Tennessee, you can see it's got 4 E's, 2 S's, and 2 N's. Okay, and we can't tell one E from the other, or one S from the other, or one N from the other. Okay, so we need a special way to count permutations there. Okay, so here's what we're saying. In how many ways can the letters in the word Tennessee be arranged? So we have how many letters? We have 1, 2, 3, 4, 5, 6, 7, 8, 9 letters in Tennessee. Okay, so if the 9 objects in the permutation are not all distinguishable, so that means, let's say we have some number of the first kind, some other number of the second, and so on. Okay, then we need to use this special formula for figuring out permutations. Okay, so again, we can't use NPR when we have indistinguishable permutations. Okay, so in this formula here, this N in the numerator is the 9 that are the total number of letters in Tennessee. And these little N sub 1, 2, and whatever in the denominator are the repeating letters. Okay, so let's say N1 is the 4 E's. And let's say N2 is the 2 N's. And let's say the next N is the 2 S's. Okay, so here's what this formula would look like. Okay, again, I'm not sure why they put this in. They said 1t. Okay, you don't need the 1 factorial because 1 factorial is 1. It's not going to change anything. Just the letters that repeat more than once. Okay, so here's the repeated E's, here's the repeated N's, and here's the repeated S's. Okay. Now, how would you enter this into your calculator? Okay, if I were doing this on a TI, I would use alpha y equals to get a fraction template. And then I would use the factorial symbol. Okay, so basically, here's how I would go about doing this. Let me first say numerator as total number of letters, factorial and factorial. Okay, denominator as the product of the repeating okay, so I'm going to have 4 factorial for the e's. I'm going to have 2 factorial for the n's and 2 factorial for the s's. Okay. All right. Everybody okay with this? Okay. So I'm going to give you a minute. Okay. Try to enter it on the TI. Use alpha y equals to get a fraction. Okay, give it a try, and I'll sit back here on the chat and see that everybody can get the right value, okay? Okay, if we go back to our slideshow, our correct value is 3,780. Okay, so I'm going to sit on the chat for a while, see that everybody can get that. Okay, give it a shot. Okay. All right, so hopefully everybody's trying it. Okay, good. All right. So how about you try this one? You try. In how many ways can you arrange the letters in Mississippi? Okay, I'm going to sit here while you work on it, and I'll work on it myself. Okay, so try it with Mississippi. There's a different number of letters in the word and different repeats, okay? So give that a try. Okay. All right, we're doing Mississippi. Let's go over to the chat, see if anybody's getting a value. Okay, I have 2 for 34,650. Anybody else getting that value? Okay. That value is correct. Anybody have questions on indistinguishable permutations? Okay, are we good there? Any questions? I want to make sure I give you plenty of time to ask or type or whatever you want to do. Okay. All right. There really isn't much to share with permutations except to be able to determine what should be counted with permutations and what should not. Okay. Again, I'm not really sure there's much of use left in this particular slide. Let me just check. Okay, good. So I'm going to switch to my notes, which are over here. All right, and I want to slide down to some of my examples for permutations. Okay. Here's my first example. And again, I don't need to walk through them because you can actually see the work here. Okay. How many three-digit personal identification numbers can be created from the digits 0 through 9 if there's this weird restriction you can't repeat digits? Now, normally, if you type in a personal ID number, like for your, say you're at an ATM for your bank account, if you want to repeat digits in that PIN, that's perfectly okay. But let's just say, so we can play with permutations, that we're not allowed to reuse a digit, okay? So what that means is pins like 808 and 777 are not allowed since we're choosing without repetition or without replacement. And the order is important. In a pin, right? Order matters just like it matters in a combination lock. The pin 123 isn't the same as 321. Even if we have the same digits in our pin, yours won't work on my bank account and mine won't work on yours. Because we're fulfilling these two criteria for permutations, no repetition and order is important, we're going to count with permutations. Okay. We have 10 possible digits to choose from. Okay. Okay. And we're selecting 3 of those. Okay. So again, you could do the business with 10 for the first, 9 for the second, 8 for the third. Or you can just say, I'm choosing from a possibility of 10 digits without replacement, and I'm only going to pick 3 of those. Okay. And if you check on your calculator, this is the same as 10 times 9 times 8. 9 times 8 is 72, times 10 is 720 different pins. Okay. So this is another example of where order matters, okay? Order also matters in phone numbers, I said already, license plates, anything that's an identifier. A password order matters. Now, usually they'd have to put the criterion explicitly that you're not allowed to reuse digits or letters, okay, in order for you to be able to count with permutations. Okay, if they don't say that, then you just have to use the fundamental counting principle. Okay, so here, take a look at this example. A TV talk show host has 4 women and 3 men as panelists. In how many ways can they be seated in a row of 7 chairs, right? He's got 7 panelists, assuming their order matters to the show host. Okay. Well, we're choosing without replacement since once somebody sits down, they're not going to get up and move. Okay. And the order is important, well, to the TV host. Okay. So we can choose with permutations. Okay. We're choosing all 7 people out of the group So we're choosing 7, permute 7. There's 5,040 ways to choose the panel if order matters and we're choosing without replacement. Now take a look at this twist. Suppose we want to alternate the men and the women in the 7 chairs. How many ways are there to do this? Well, we said we had 4 women and 3 men. So we're going to start with a woman because there'll be a woman on either end, right? If we've got one more of those. So now I'm out of permutation land and I'm just logicking my way through the problem. I wrote down W1 for the first woman, M1 for the second man, W2 for the second woman, M2 for the second man, W3 for the third woman, M3 for the third man. And here's that fourth woman out here by herself on the end. Okay, so those are the seats. And the number of outcomes, I've got 4 women the first time around, so that's going to go here. By the time I get to the second woman slot, there's 3 women left. By the time I get to the third woman slot, there's 2 of them left, and 1 for the last woman's slot. Likewise, for the men, there are 3 of those for the first man slot. Okay, 2 of them for the second man slot, and only 1 left by the time I get to the third one slot. By the fundamental counting principle, I need to multiply all these possible outcomes together to get the total way to pick a panel so that the men and women alternate. So I'm going to multiply them together, and now there's only 144 ways to choose this panel. Okay, everybody okay with this idea? Okay, let me go back to the meeting. Okay, and let's move to the situation where order doesn't matter. Okay, so again, we've talked about all the situations where order is important with, personal ID numbers, passwords, license plates, phone numbers, people on a panel, people in a line. Okay, order doesn't matter when there's nothing special about the way you choose. I know that sounds kind of strange, but let's move on, and hopefully you'll get the general idea. Okay, so here's combinations. Okay, so here's the combinations formula, and the only difference between it and the permutations formula is we're dividing out repetitions of the same combination. In other words, this is where we're dividing out different orderings of the same things. Okay, so in general, because we have this extra term in the denominator, there are going to be fewer combinations than permutations of the same 2 N and R values. Okay, again, we are not going to use this formula. We are going to use either the TI-84 or Excel. Okay, so again, they're showing you NC3 is 56. Okay, so again, what I need you to do is we're going to try this on our TI. Okay, type. Okay, that value was 8C3. So we're going to type 8. Then we're going to go math, EROB, then NCR, type 3. Okay, so I need you to try this as soon as I get it up in the chat box. Okay, type this. Okay, so combinations is on the same exact menu in the probability section of math. Okay, so type your 8, math, go over to probability, NCR, and 3, and everybody getting 56. Okay, everybody needs to try it so that way I'm sure you can use your calculator for homework. Okay, 56. Okay, good. Excellent. I will also show you how this works in Excel. Okay, here's my Excel spreadsheet. I'm going to go over another column, and you can see there's a combinations. It's called combin. Okay, it returns the number of combinations for a given number of items. Open parentheses, and you get the same two arguments, the number you're choosing from and the number you want to choose. Okay, so our example was 8, choose 3, and there's our 56. Okay, remember, again, once you see the number in the cell, you can just go back and click on it and you'll see the formula in the formula bar. If you need to change the formula, do it up here on the formula bar. Okay. All right, let's take a look at some uses, like actual examples with combinations and combinations. Yeah, let's do combinations. Okay, if they don't have good ones in the slides, we're going to go back to my notes. Okay, now here's an example of how combinations would work. Okay, if I'm forming a committee of 4 people from a group of 10 people, is there any difference in the way, does the order in which I choose people matter? It doesn't, because at the end of the day, they're all going to wind up on the committee. In other words, nobody has a special job. If you said you were going to choose committees of 4 people, and the first one was the president of the committee, the second one was the treasurer, the third one was the secretary, then you're putting an order on the choice because they're going to have different jobs when all is said and done. But in this example, okay, you can see I'm choosing people without replacement. Once I pick you to be on the committee, you're on the committee. Your name doesn't go back in the hat. And the order I'm choosing you in is not important. Okay, it's an unordered group of people, so we're going to use the combination of 10 things taken 4 at a time. Do not worry about this. You are not going to do it by hand. You're going to use technology. So let me go over to the notes I'm creating over here. Not those notes, these notes. Hello. Okay, and we're going to talk about combinations. Okay, and in other words, in order to use combinations, we have to be sampling without replacement. An order in which you choose is not important. Okay, so in our example, we're going to use NCR. Okay, and you know where that is on your calculator. So in the committee example, let's just do that as a separate thing. Okay. Choosing 4 out of 10 people. Okay. So the total number of people I have to choose from is N, right? So N here is 10. I'm choosing only 4 of them. So R is 4. So calculate 10C4. Okay, why don't you try that? You calculate 10C4, and then we'll type in the answer. Okay, so calculate 10C4, and I'll do the same thing. Okay, let's go back to the meeting, see what you're doing. Okay, we're getting a couple of people getting 210. So 10C4 equals. Okay, everybody able to get that result? Again, you can use the TI or you can use the combin function in Excel, whichever works for you. Okay, it is a good idea to get familiar with what's available in Excel. It has a very, very rich set of features. Okay, I'm going to wait a while to make sure everybody can get 210 out of this. Okay. All right, let's see what's left. Time-wise, we've got maybe another 20 minutes tops. Okay, I don't want to keep you longer than you need to be here, but I want to make sure everybody's comfortable with the idea. Okay. Okay. Now take a look at this one. From a class of 15 students, a group of 3 or 4 students will be selected to work on a special project. In how many ways can a group of 3 or 4 students be selected? The key word in here is 4. Okay. The first thing you want to stop of whenever you're choosing like this, you want to ask, am I choosing with or without replacement? Well, in this example, I'm picking a student to be in a group, and once I pick that student, he or she isn't going to wind up in a different group. So I'm picking without replacement. Okay, the second idea is, does the order you choose them in matter? Well, in a specific group, it doesn't, because basically if I choose 3 people to be in group A, then they're all in group A, and the order I chose them in doesn't matter. So I'm choosing without replacement, and order doesn't matter, so I'm going to count with combinations. I'm going to count the outcomes. Okay, so let's take a look at this. The number of ways to select a group of 3 students from 15 is 15C3. They're using this notation because it's hard to write the other notation in a slide. Okay, but this is a combination of 15 things taken 3 at a time for 55. They do the same thing with a group of 4 students. Okay, there are a lot more combinations you can make if you add another person to the group. So that gives you 1,365 students. Now, I have a question for you. Where'd they get the 1820 from? Can anybody figure out, looking at this slide, how they said the total number of ways to select a group of 3 or 4 students will be 1,820? Where did this number come from? Anybody have any ideas? The key word here is or. Okay, and if you remember from our previous work in probability, whenever you're talking about oring things, you're going to add. Okay, why is that? Well, oring gives you alternatives. Okay, and it makes the number of possible outcomes grow. Okay, so the way they got the 1820 was they added the total number of outcomes of 3 group students plus the total number of outcomes of 4 group students. So 455 plus 1365 is 1820. Okay, and again, the trick to realize here is that or means add. Okay, I'm going to put that in our notes. Okay, so we got 210. That one. When you want the number one event or another, add outcomes. When you want the number of outcomes, one event and another, multiply. Okay, this is the multiplication principle. Okay, everybody understand what I just typed. Okay, that when you're ORing outcomes, you're adding the possible numbers. When you're ANDing them, you're multiplying together. Does that make sense to people? Okay. Right. So some of you are saying it's making sense, and that's good. That's great. Okay. All right. Good. 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 All right. Let's see. We probably want to see if there's anything different in here. I'm going to just scroll down. Okay. Take a look at these two examples here. Okay. This one's saying how many 4-digit code numbers are possible if no digits are repeated? This is kind of giving you the opportunity to decide which should you use, permutations or combinations. Now, if you take a look at it, they're calling them code numbers. So you must think that they might be some sort of a password to get into something. Because of that, the order of the digits matters. In other words, 1, 2, 3, 4 is a different code from 4, 3, 2, 1. Also, they're telling us we're not allowed to repeat digits, so we're sampling without replacement. Okay? Because we're sampling without replacement and order matters, we're using permutations. We're taking 10 possible digits. Does everybody understand where the 10 is coming from? Okay. For each digit in the code, you have 10 possibilities, and you're picking 4 of those without replacement. So there's 5,040 numbers that you can pick as codes. If you take a look here at part B, a sample of 3 light bulbs is randomly selected from a batch of 15. How many samples are possible? Well, if you think about it, I've got 15 bulbs and I'm going to pick them for my sample and I'm going to test all of them. There's no difference between the first one I pick and the second one and the third one. They're all going to be tested for defects. So the order I pick them in doesn't matter. However, I am picking them without replacement. In other words, once I pick a bulb to test, I'm not going to put it back in the batch. So I'm sampling without replacement. So sampling without replacement and order does not matter or is not important means you count with combinations. Okay, so here I'm going to count 45 different possible samples. Okay, do these two examples help you distinguish between permutations and combinations? Okay, do those examples help? Okay, because the next thing we'll do is I'll put 2 examples on the Word document and see if you can figure them out, okay? And this will probably be the last thing that we do today, since we're coming up on time for a meeting. Okay, so you try, okay? Here's the first one. I'm going to scroll down a bit to fit it all on. Whoops. This is very jumpy, this interface. Okay. Um, To attend. Okay, there's the first one. And what I need you to do is decide NPR or NCR or neither, and solve. Okay. Okay, so as soon as they come up on the screen, you can try. Okay, so here are my three questions. Hopefully you can all see them. Okay, a manager wants to select 5 out of 12 employees, her 12 employees. Okay, and to attend a conference. And how many ways can she do this? Decide if you're going to use NPR or NCR or neither, then solve. Okay, I'm going to take these directions and put them out here. Okay, so for all of these, this is what you want to do. You want to decide, do I count with permutations, combinations, or neither? And then try to come up with an answer. Okay, I'm going to leave these up here. And see if I can get back to the chat. Maybe I can make this a little smaller. Let me see if I can do that. Good. I can see the chat now. That's great. Okay. Can you still see the screen with the questions? Okay. All right. So let's see if we can come up with answers to these three questions. Okay. Remember, you've got to ask yourself about replacement and order before you can make the choice. Okay, I've got some answers already. Okay, let's take a look. All right. I'm going to give you a few more minutes for everybody else to give it a try. Okay. All righty, so we've got some answers all over the place. And that's good. Okay, at least you're giving it a try. That's the main thing. Okay, let's work on these together. Okay, because we're kind of running out of time. All right, I'm going to switch to, hopefully you can see if I type in red. Okay. Okay, so a manager wants to choose 5 out of 12 employees to attend a conference. Are we choosing with or without replacement? Well, this is without replacement. because basically once an employee is chosen, they're not going to wind up back in the pool, okay? Also, everybody that gets chosen, the 5 employees, are going to attend the conference, so order doesn't matter. Okay? Because of these two things, I'm going to use NCR to count. Okay, and in this example, I'm going to have 12 C5. Okay, and let me just do that on my calculator. Hopefully everybody's doing that with me if you haven't already done that. And 792, I do remember seeing that in the chat. Okay, there's that one. Okay, a batting order is the order that the players come up to hit the ball. And we're saying batting orders are important. Okay, I kind of said that order matters in a batting order. Okay, also we're choosing without replacement. Okay, so once we pick somebody to be in the order, that player can't be in the order in a different spot. Okay, so we're choosing without replacement. And we did say order matters. Okay, so we're going to use NPR count. Okay, we're going to use permutations because the order matters, right? So again, I have 13 players I'm choosing from, and I only want to choose 9 of those. So this is 13P9. Okay, so let me do that real quick. You do it with me. And that's a really big number. It is 259,459,200. Okay. Now, for those of you who know something about baseball, you might be looking at this saying that's the stupidest way in the world to choose a batting order because you choose it based on player capability. I understand. In these examples, we're making the assumption that all of the choices are random. So coach is going to put the 13 names in a hat and draw 9, okay, which is not the way a real coach would choose a batting order. Okay, I understand. Okay, but we have to do random sampling here. Now let's take a look at this last one. A license plate for a certain state has 3 letters followed by 3 numbers. How many plates can be made? I didn't say anything about not reusing numbers and letters on a license plate. And in general, numbers and letters on plates can repeat. Okay? So I can't use either permutations or combinations. Okay? Since they require that I sample without replacement. If I'm going to be able to reuse letters, I can't count either of these. Okay? So I have to think about how to do this. Okay? I'm going to have letter slots. So let me call my letter slots A. So I have 3 letter slots followed by 3 number slots, okay, on this plate. For each letter slot, I have 26 possible choices because there's 26 letters in the English alphabet. And I'm allowed to repeat them, so I have the same 26 choices for each letter. For each number, I have 10 digits to choose from, and I get to repeat those as well. Okay, so this is the total number of license plates I can have in this state. Which again is a really big number, 17,576,000. Okay, so again, let's take a look at this, and I'll ask, does anybody have questions? Anybody having a problem with any of these 3 examples? Okay, any questions? Okay. Giving everybody a chance to check in. It looks like you're all doing really well. You're all getting the right answers. Again, the point of these is not to see if you can calculate, but that you can actually figure out, do I use permutations? Do I use combinations? Do I use neither? Okay, that's important, because once you can figure that out, you can do it in Excel, or you can do it on the TI or any other app. Okay. All righty. So good. I was just wondering if you can upload. I will definitely upload the document. Okay, I will upload the notes and video. Any questions? Okay, before we sign off, I just want to ask, is everybody okay? Anybody questions? Okay. Second thing, does the WebEx format work for you? Okay, WebEx format working for you? Okay. Okay, anybody using phone app? Okay. Anybody using the phone app, or are you all using it on a laptop or tablet or? Okay. I just want to make sure the phone app has all the functionality. Okay, phone app. Okay, Jose, thank you. Okay, and you were able to see everything and hear everything, right? Okay, good, good, good. All right, you're a desktop app, good. I'm on a laptop, and you are in my kitchen. So what you're seeing behind me is my kitchen. I don't know about you, but I know when I was in school, I did all of my math at the kitchen table. So here I am back again doing math at the kitchen table. So again, I'd like to thank all of you for being here. And I will see you again on Wednesday, same time in WebEx. So look for a WebEx invitation on your Maricopa email. Okay? So again, whenever you're ready, feel free to drop out of the meeting. We are done. See you Wednesday.